Alright, hey guys, what's going on? So today we're going to be talking about the electromagnetic self-dual bivector. So we're starting to put a lot of things together, and then with these tools we're going to be able to understand how to implement this into a Lagrangian formalism and how to implement it into the electromagnetic stress energy tensor. Okay, so we started from bare bones. We started from recapping what electromagnetism was, how it was formulated, and we're gradually getting up to a point where we will be able to implement electromagnetism into the stress energy tensor. And the stress energy tensor, as you know, is on the right hand side of the Einstein field equations, and as you know, those are the fundamental equations for general relativity. So without further ado, let's get straight into the content. Make sure to hit that like and subscribe button also, and make sure to go onto my Patreon page if you want to support the channel and get notes and supplementary notes to everything that's going on within this playlist. Alright, so let's get into the topic. So we are talking today about the electromagnetic self-dual bivector. What this is, it's a special type of bivector that contains real components and the dual components. Okay, so we talked last time about how these dual tensors were sort of related by means of a complex number. Okay, and we're going to take advantage of this, and we're going to keep on going forward with it. So the self-dual bivector, as we mentioned before, is this object right here. Why is it called a self-dual bivector? It's because it's got the dual within its definition, right? So the dual right here is this, what we called right here. Then we have this, which is not the dual, and then this is something that contains both of them. Okay? So the self-dual bivector for the electromagnetic field is going to be completely real, because when we multiply this or by the upper indices, we'll find out that excuse me, we can effectively get rid of the complex part. Okay. In an inertial frame, also, the forward velocity is u mu. Okay, and we're gonna, if we define this u mu as the forward vector or the forward velocity in this way, in which you're just traveling through time, not through space, the electromagnetic field acting on this velocity gives us these rules of multiplication. So this here is our matrix. This f mu nu is this matrix, and then our u is our velocity vector. So the matrix applied to the velocity vector, this is just simple matrix vector multiplication. We get this. Notice that this is the electric components of the electric field, right? We have the x, y, and z components. So f mu nu acting on u gives us the electric components, and then the dual gives us the magnetic components, right? So this is interesting, right? Because the idea here is that we have a real part that's associated with the electric field, and then we have the dual part, which is associated with the magnetic field. Put those together in a complex way, and you get the self-dual bivector. Okay, now let's take a look at this self-dual bivector a little bit more. So the electromagnetic self-dual bivector acting on the forward velocity vector gives what we will call an electromagnetic forward velocity. And let's take a look. We're going to call it this, right? This isn't something that you typically will see in books. I just sort of named it this way just to get a few things straight here. So the idea here is that we have, so we're going to act on u, okay? And so this whole thing is going to give us, because this contains this and this in it, it's going to give us the electric components. That's the real part, as we just saw. And then the dual is going to give us the magnetic components. So these are two vectors, okay? So these are two vectors, and what we're going to do is we're going to call this f mu, right? So the idea again is this acts on some vector, so you can almost think of this as a contraction. This is nu and this is nu. So what we're left with is mu, which is this vector right here. So it's a vector that lives in complex space, right? But it's weird because, right, if we're thinking about complex space, typically we have imaginary and real components, but the components themselves are vectors, okay? That's a vector and that's a vector. So any point in this plane, right, so you have some vector in this plane, this is described by E mu B mu, right? So these two things are vectors. They're not really space-time points, which is how we're going to be able to distinguish, which is how we're going to be able to understand how electromagnetism is implemented into GR, okay? So let's just keep on going with this. So what we can do is we can say, well, if this thing contracts indices, this thing, we can add an index to get this thing back, right? So we have mu, this is our vector, our velocity vector, right? And so this here is going to give us the electric component. And then all of this, I highlighted just this part in blue, but in reality, as you recall, this whole thing, not the I part, this whole thing here, we defined as being the dual, okay? So this is the magnetic part, and this here is the electric part, okay? And so electric part, magnetic part, and so F mu nu, therefore, when we multiply everything out, we're going to get, so mu F nu, so this is F nu, right, because we defined F nu as this vector, right, here, I'll just do this. Sometimes it starts getting a little bit confusing and clustered when everything is on the page, when all my writing is on the page here. But the idea, again, is, so okay, I think I misspoke a little bit. I called this the electric part. Not really, right? Because this whole thing is the real part, not the electric part, right? So this is the real part, this is the dual part. So the not dual part and the dual part, and then when we plug F nu and F mu in, we get this, and then we also get that same thing, right? Because this is just different indices, right? Mu, right? This mu and mu, nu and nu, and this thing, same thing. We add. Let's see here. So we could take mu, we're taking mu out, and these two things are going to be, let's see, so this is going to be 1/2, right, because, let's see here, rho sigma, sigma rho, sigma rho, okay. So we're taking the mu out, or the velocity vector out, okay. So this is what's going on here. We're taking these two guys out, calling it a single. We're calling that rho, okay. If we're going to do that, we call these sigma, okay. So this is really just a change, swapping indices here. And when we do that, so really what's going on here is, just to make things clearer, is that we're swapping these guys, right? We're swapping those indices. And we can do that because they're just dummy indices, right? So these things are just dummy indices, and we get this guy right here, okay? And then what happens is we say, so E nu, here's E nu, and E mu, right? And then we have this minus sign. And then we have this part here, right? So this part here multiplied with I, that's going to give us -1, which gives us this here. This is all the real part, right? Because then we get B nu and B nu and B mu, okay? And then the rest of this with the E in the component, in the complex component here. Or not the complex, right? Because we have, this gets factored out. So we have this I, and this I, which gets factored out here. And so we have this. So what ends up happening is that F mu nu has a real part and it has an imaginary part. Right? So we're defining all of this here to be this right here. And we're defining all of this to be this right here. All right. So again, so the point here is really just to see that we now have defined this and this guy, and we've defined this guy. Right. So these are all in terms of the electric field and the magnetic field. So we have F mu nu, we have F dual mu nu, and we have F mu. Okay, and then we also have F dual mu. Right, F dual mu nu is going to be, that is going to be complex, right? So that's going to be where this guy's a minus sign. All right, so we have all these objects. They live in some space-time, right? So here's our space-time. And they all exist in their own space at some point in space-time, and which is what I'm going to try to illustrate right here. I only do it with two of them, right? Because I kind of just gleaned over this. I kind of assumed, when I was making this, I think I kind of assumed that you can just really not think about this guy right here. It can all be encapsulated into one object, which is, again, these two guys. So you don't really need to do this, because these, you obtain those guys, you obtain these from these more fundamental objects, which are the bivectors, or the tensors, if you will. All right, so on a manifold, these electromagnetic field bivectors and the dual magnetic field bivector act on the time-like vector. All right, so that time-like vector, again, being this forward velocity. Okay. And the gradient of the electromagnetic self-dual bivector encompasses the homogeneous and inhomogeneous Maxwell equations, which is these guys right here. Okay. And again, these guys here form our electromagnetic self-dual bivector. I try to make this curly because when I typed it out, it looks curly. However, my handwriting is not as good as typing. So this is, again, the self-dual bivector. Right, so all of this can be encapsulated into one tensor space, the cell of the self-dual bivector. Because this thing exists everywhere in space. It's a function of space-time. Okay, let's continue. So we can now calculate the quantity when they're contracted, right? So when we do that, what we're doing is we're just contracting up lower and upper indices. And when we do that, we get all this, and we see some things are going to add together, right? So this is going to add with this guy, right? And this is going to add with this guy, right? And we get these right here. The green quantities are Lorentz invariant objects, recalling the formulas for F mu and F, the dual F mu nu. Okay? So these guys are Lorentz invariant objects. Okay? Or these things are the building blocks of Lorentz invariant objects. Okay? Because now we can contract things. We can calculate the first invariant object, this one. So we just plug things in where everything's lower index, and then here everything's upper index, and we do that. We get all of this garbage in here. And so this actually will reduce because this is an anti-symmetry property, right? So mu rho, mu and rho, this, due to anti-symmetry, whenever you multiply things like this together, you actually get 0. Well, I don't want to get too much into this, other than to say that whenever you have something like the Levi-Civita symbol, and you know it's anti-symmetric, and these two things are symmetric, when you multiply something that is anti-symmetric with something that is symmetric, you get 0. And you can sort of think of that almost intuitively, because if you think of a matrix, say, that is anti-symmetric, so say you have zeros along here. Anti-symmetric means that you have negatives over here and say positives over here, and then something that's completely symmetric, again, you have zeros, and a lot of this is actually going to go to 0, so you have something that's completely symmetric. Again, I'm not going to go into like a huge calculation on this. I think it might be kind of interesting to do that just to prove this. But again, the idea here is that when you have something like anti-symmetry, you have this relationship here where the anti-symmetry thing multiplied by two symmetric things, or multiplied by something that's symmetric, gives you 0. I realize I kind of brushed over that because I don't want to spend too much time on that. What I will do is I will make myself a note and I will go more into this if this is something that you want to see. The U vector is also time-like, so that's this condition. Again, something that I want to go more into, but I think it will take another video to do that. And it's not really within the purview of electromagnetism itself. It's more within the mathematical framework of how GR and special relativity works. But the U vector is also time-like. That is the same thing as what I just typed right here. So that's my mistake. But the point here is that we want to employ this condition where you look at this guy here. Here's our E mu. Well, no. Right. This here is our vector, right? And when we multiply that by E mu, well, that's going to be that you can have a bunch of numbers, right? This is, say this is you have some number here, You have some number here, and you have some number here. The point is, this is going to be 0, right? Because we have these components, right? So these multiplied by this, you can see how this is going to be 0, right? These 3 are 0. This is a number. This is 0. These 3 are numbers. Okay. So the point here is that that actually equals 0. I'm extrapolating my explanation too much here. Or I'm trying to explain this a little bit too much in detail, I think. But when we see all this, and when we have this, then we get, this actually reduces, we can reduce the invariant quantities to this, and then this further reduces when we take all of these Kronecker deltas to something like this, right? And so, and the reason for that is because again, these are dummy indices, which is going to give us -2, and then these guys here, well, these are just going to take we're going to have sigma, right? So let's see here, kappa, lambda kappa, rho sigma, right? So kappas are going to go to sigma, and that's what these guys are, and rhos will summate with the lambdas here, and what ends up happening is that this guy becomes sigma, right? So this guy becomes sigma. That's what these two guys are doing. This guy and this guy. So that's going to make this guy sigma. And then this guy and this guy is going to, we're going to keep that, let's see, rho to kappa, rho, so kappa to rho. So these two guys are going to sum over each other. But if you recall, we have this, right? And so what this ends up reducing to is all of this. Okay. So we have this. The invariant, therefore, is going to be this guy, right? Because these are just, this is b squared, this is e squared, right? So we get this, and then we get the invariant being, this is our first invariant. All right, so similarly, so the other invariant can be reduced to this right here. So I'm not going to go through that calculation just because that'll take a while. If that's something that you want to see, I can definitely do that. But I don't want these videos to go on for too long. So a total contraction of the self-dual bivector is therefore given by this, right, which is this here. Right, because if you recall, we have this 2, and then we have this 2, which is why we have 4s. Okay, so everything gets multiplied by 2, so that's where this guy comes from. And then we get this. So the complete contraction of the self-dual bivector, this is a contraction of the self-dual bivector is this guy. And so this is an invariant quantity. This is invariant. This is an invariant object that doesn't depend on how you rotate your spacetime. Invariant under Lorentz transformation. So I'll say under, and I won't put this in quotes. It's invariant under Lorentz transformations. All right, so again we have the magnitude of B, the magnitude of E, and then a dot product between the two. So you can sort of think of this as like, so say you have your electric vector and your magnetic vector. The magnitude, so the magnitude again is the length of the vectors, right? Oop, wrong thing. So that's the magnitude, and then you take the dot product, and then you can combine those the dot product becomes the imaginary part of this invariant object. Okay. All right, so we've set the stage now for understanding a little bit more electromagnetism in this picture. What we're going to start doing now is we're going to start piecing things together and putting this into this object, right? So T mu nu. And if you recall our Einstein field equations, G mu nu proportional to T mu nu, again because of the Bianchi identities. But I'll just say because we found this to be the case, and we know that this is also the case. And you know what, we need to do some contraction here. So we found this to be the case and this to be the case. And so the idea here is that the curvature is, and T mu nu are very similar or proportional to one another. So the degree of curvature tells us the degree to which there is mass that's contributing to that curvature. But the claim here is that electromagnetism will also do the same thing. So an electric field and a magnetic field also warp space and time. And so that's going to be how we're going to tackle the problem of electromagnetism when it starts coming to talking about not curve solutions, but when it comes to start talking about how magnetism plays a role in black holes, right? So the famous case, or one of the famous cases, is the Reisner-Nordström. I believe there's two dots there. Don't quote me on that metric. And what we're going to do with this metric is we need to define our metric, right? So our metric is going to have, we're going to set this side of the equation here. We're going to set this side of the equation to have electromagnetism in it. So fundamentally, the metric is going to be a function of the electric field and the magnetic field as well. So we're going to have, when you write out the metric in matrix form, there's going to be E's and B's everywhere in this matrix. Okay, and the electric field again and the magnetic field play a role in the curvature of spacetime, which is eventually what we're going to get to. And, this also isn't. What I will say also is that we're not going to just talk about this, right? We're going to talk about some other things within GR, because I want this to be like a comprehensive playlist on GR. So once we're done with this, we're going to be talking about also conformal invariance. And this is going to get us into the topic of the Weyl tensor. we're also going to look at the Weyl tensor along with the Lanscoz, I think that's how you say it, Lanscoz conditions. There's a thing called the Lanscoz tensor, which plays a role in this Weyl tensor as well. And then we're gonna we're gonna talk about electromagnetism. We're gonna talk about conformal invariance. We're also gonna talk eventually about how quantum mechanics might play a role in this curvature, but that's going to be later on down the line. So this is all to say. This is all to really just say that we're sort of motivating ourselves to getting towards talking about solutions to the Einstein field equations. We're going to talk about a lot of different types of metrics, the Reissner-Nordstrom metric, the Schwarzschild metric, which is the famous metric that you typically go over before you get into anything more advanced. I really just want to get all this electromagnetism done first before we start talking about these metrics. So with that being said, make sure you hit that like and subscribe button. Make sure to go onto my Patreon page if you want to support the channel, and also if you want to get notes. With that being said, I'll see you guys in the next video. Bye.